Hello students. Today I'm going to do the second case of delta function potential well. That is when the energy is positive and the solutions are scattering type. So we have potential well of type Vx is minus alpha delta x. That means this is my potential. Vx is a function of x. Now my particle energy is here, that is E is greater than 0. Here we have 0 and our particle energy is E is greater than 0. Now for this type of potential, I have to solve the Schrödinger equation. So Schrödinger equation, we know Schrödinger equation is minus h cut square 2m del 2 psi upon del x square. Then you have a potential Vx psi x equal to E psi x. This is my equation, and now I have to write this equation. So this is my x0. So I will write this equation for two reasons. I call this reason 1 and this time I call this reason 2. So now for reason 1 and 2 both have potential 0 because delta function has a value only at x0. So this equation now is 2m del 2 psi upon del x square plus will be minus alpha delta x psi x e psi x. Now for x less than 0 reason, that is the reason first, this equation becomes minus h cut 2 del 2 psi upon del x square. This terms become 0. So you have only e psi x because delta has the value only at x is equal to 0. So this is the equation, and now I can solve this equation. This equation gives me del 2 psi del x square, and now this becomes 2m e h cut square minus psi x. And this is a very well-known equation. If I write here del 2 psi upon del x square equal to minus k square psi x. The solution of this equation will be, I'm writing the reason 1, psi 1x will be A is a simple harmonic motion type of equation. So this will be solution will be e power iota kx b e power minus iota kx. These are the solution. Similarly, if I write for region 2, also equation remain the same. For x greater than 0 also, the region 2 also will be the equation same, and this time I write the function as instead of a, b, c, d, or you write f e power iota kx plus g e power minus iota kx. Now, this is your incident wave, x less than 0. So this is, I'm writing here, so you have an incident wave, say a e power iota kx is an incident wave here, and this is your reflected wave. So if I say this is my x-axis, this is incident wave, b is reflected wave. Now deflection generally happens through the barrier and classically, but quantum mechanically, well also can give you the deflection. That is the difference between two theories. So you have this is a reflection part, and once if you come to the x greater than 0, if I say this is my transmitted beam which is also moving in the plus x direction, now here you can't have a g because there is a nothing for another well potential for this reflection. So I'll take so we cannot write here g should be 0. So g should be 0. So I'm removing this here. So we have only transmitted flux. So this is my 2. Now we have the equations. Now we have the wave functions, and now we want to solve these wave functions. So what I'll do, I'll put the boundary condition. So at x is equal to 0, both should match. So x is equal to 0, psi 1 to psi 1, 0 should be equal to psi 2, 0. Now psi 1, 0, put 0 here. So this become a plus b, and this become f. So this is my first relation between constant a, b, c. Now the next question is, what is the second condition? Second condition, we can apply discontinuity of first derivative of wave function, because as in my last class we have seen, here your first derivative wave function cannot be continuous. Okay, so psi should be always continuous for acceptable wave function, but the first derivative only is continuous when your potential is piecewise continuous. So here is infinite function, so this will be discontinuous. And then I told, we were discussed in the last class, the condition discontinuity is equal to psi dash x at x is equal to 0 minus psi dash, this is the first differentiation, psi 1 x 0 is equal to minus 2 alpha m alpha h cut square psi 0. This is my discontinuity condition we have derived in last class. So now we can just put the values here. Psi 1 at x, psi 1 dash at x equal to 0, psi 1 dash. So if I differentiate this equation and put x equal to 0, what will come? Is a iota k, and this remains same, put this 0, and this become minus iota k b, and this becomes 0. So this gives me iota k equal to a minus b. And similarly, if I write psi dash second wave function at x is equal to 0, so you have only differentiate this one, this become iota kf. So this become iota kf. Now just put these values in this equation and we'll get the second condition. So we have a iota kf, okay, iota kf. Then you have this is here iota kf minus iota k, this is a minus b, and then you have minus 2 m alpha h cut square psi 0. So psi 0 is what? Psi 0 is a plus b or f. Psi 0 is what? A iota kx plus b iota minus kx psi. Put 0, so it's become a plus b, which is again equal to a b. So here I'm writing a plus b, or you can write f also. But I want to solve it for say I want to remove one constant here. Now I have here iota k. Okay. Now just I can solve it further. We have iota k, and this is equal to a plus b. F is a plus b, and then you have minus a plus b, and this is equal to this thing. Okay, and this gives me a cancel, so this gives me 2b iota k, and here we have minus 2m alpha h cut square a plus b. So 2 cancels out. Okay, 2 cancels out. So b becomes minus is iota square m alpha h cut square k iota iota cancel, and then you have a plus b. So my b becomes m alpha h cut square k a plus b into iota. Now I write this as a constant. So my b becomes now iota beta a plus b, where beta, you have to remember, beta is m alpha h cut square k. Okay, beta is m alpha h cut square k. So from here now we can solve for b. So b comes out iota beta a upon 1 minus iota beta. This is a relation between b and a. Similarly, now I know f is equal to a plus b. So now I have a, I want to remove b, so b will be equal to iota beta a 1 minus iota beta f, and this gives me a iota beta a plus iota beta a upon 1 minus iota beta. So this is relation gives me, this cancels out, these two terms cancels out. So it is simply a upon 1 minus iota beta. So we have a b, we have a f. F is your 1 upon 1 minus iota beta into a. So we have a two constant. We have a relation between a, b and f. Now I want to find that reflection constant and transmission constant. So reflection constant is defined as J incident upon, J reflected upon J incident. Similarly, transmission constant is defined as a J transmitted upon J incident. And now what is the equation for J? Suppose I want to find J incident or J and J. The equation is minus iota h cut upon 2m psi star del psi upon del x minus psi del psi upon del x. From here, I can find the J incident. Now we know what is, if you solve this one, J incidence, we know the function in region 1. So J incident is with e power plus iota kx. And if you want to put t, so you can write omega t also, this xt. So J incidence is basically a e power iota kx minus omega t. Now just differentiate this one. So if I differentiate this one, this will give me iota h cross 2m. Psi star is a star, and psi I differentiate. So this will give me a psi star psi. So a mod of a square. Okay, and iota k will come more. And this iota kx minus omega t, or psi star minus iota kx omega t, and that will be cancelled out. So you will have only a square, this one minus here, and similarly here. Now psi star, this is psi 1 and psi 1 star. Psi 1 star is what? Psi 1 star is a e power minus iota kx minus omega t. So again, if I differentiate this one, I'll get minus iota k, so minus minus, uh, this psi will be there, and this will be minus minus plus, so iota k, and again mod of a square. So if I solve this one, this gives me iota square minus cancels out, so this will be h cut k mod of a square upon 2m, and this will be 2a square, so 2 cancels. So this gives me h cut k upon m mod of a square, j incidence. Similarly, I can find j reflected also. So j reflected will be simply same like h cut upon m. Now his reflected part is this one b. So he'll come minus mod of b square. We can solve it here, and the g transmitted will be moving positive direction. Flux is moving in positive direction, so this will come at h cut m mod of f square. So now I have calculated all the fluxes. Now let us calculate the reflection constant. So reflection will be j reflected upon j incident mod. Okay, to take mod, so this will come out a upon so b upon a mod square. H ka time cancels, and when mod we take, minus sign will also cancel. So we have only this one, and transmission coefficient will be f upon a mod square. Now reflection b by a we can calculate here, we calculate mod. So my r will become beta square upon is 1 under root 1 plus beta square. So this becomes 1 plus beta square. And now we know this I can write as a 1 plus 1 beta square. And beta already we know what is beta. Beta is our m alpha h cut square k. And if I now square it, this become 2, 2, 2, this become 4, and this become 2. And k square value already I know, alpha square, k value is h cut 4, k is 2 me upon h cut square. So h cut cancel, you have a square only here. And now you have m beta square is 2me. I want 1 plus beta square, so this will become 1 upon 1 plus, so beta square. So this will be 2me, 2m also should be cancelled. 1 minute. This is, so you have a m square alpha square 2me, so m also cancels. So here you have only m only here. Okay. So this is beta square. So 1 by beta square will be 2 2e, m cancels out, 2e 2e, and then you have here m cancels, you have h cut square also remaining, 2e h cut square m alpha square, m alpha square. This is your reflection constant. Okay. And now So as energy increases, reflection becomes less. Okay. Now similarly, we can find the transmission coefficient. Transmission coefficient. So this is equal to f upon a mod square, and which is equal to 1 upon 1 plus a beta square, because f upon b is 1 plus 1 minus iota beta, and beta we have already, beta we have only m alpha square. Okay, m alpha square 2 e h cut square. So as energy keep on increasing, my transmission constant tends to 1. Okay, so if is e goes so infinite, my transmission goes coefficient becomes 1. Okay, and here it is opposite. If e is tends to 0, then r tends to say, if e tends to infinite, transmission constant becomes 1, and here if e tends to 0, reflection becomes 1. So these are the expression for transmission and reflection coefficient at infinite potential well, E greater than 0. So here wave functions are not like a traveling wave; they are not normalizable. So the solutions are called scattering solutions. Okay, so I will stop here. In next class, we will see another type of potentials, one-dimensional potentials. Thank you very much.